luckily my flight did not get canceled. I did take a 14-hour flight to get here from New York. So it was pretty close, but I'm here now. I'm going to be here for the rest of the week.
Yeah, so with that, please take it.
Yeah, sure. So my name is Jespersen, and I'm also a final year graduate student at Princeton, where I work primarily with Peter Melchior and Nick Kragh. I primarily care about galaxies, and one of the things that you want to think about when you start writing a thesis about galaxies is what kind of data am I going to use? That's because conventional wisdom dictates that depending on what things you want to investigate about galaxies, you have to use different kinds of data. If you want to learn something about stars, you have to look at the optical. If you want to learn something about dust, you have to look at things like the mid-planet breadth. Additionally, you might also want to think about whether or not you're using images, spectra, because those just, again, conventional wisdom dictates that will just give you fundamentally different views of your galaxy. So for my first thesis committee meeting, where I had to sit down with 5 professors and define what I was going to be doing for the next 3 years, this was exactly the first question that was on the docket. What kind of data are we going to use? So my pitch was to use optical spectra. After all, everybody knows that optical spectra are very big or rich, and most importantly, we have them in abundance. Of course, the second I had said that, one of my thesis committee members then objected, saying, no, like, you're fine. But there's just so much about galaxies you will never know unless you have access to the infrared. Somebody else in my committee then objected to the first objection, like, no. There's actually, it should be fine. Most of the things you want to know about a galaxy, including the things that you get out of having access to something like mid-infrared photometry, is actually already included in the optical spectrum. And so my thesis committee meeting that was supposed to be about my thesis quickly went from being that to being a fight about the question, how much can I tell about the infrared emission of a galaxy, given that I only have access to optical? So as I mentioned, this is a question that sent my thesis committee into 2 distinct camps. With one camp arguing very strongly that, like, obviously you can tell whatever you want about the infrared emission of a galaxy starting with optical. One camp arguing that you definitely cannot do this. This is an interesting question to think about because, in general, it reveals a lot about what assumptions we make about how galaxies work. Therefore, I think it's worthwhile for everybody here to just take a second and try to think about what your answer to this question would be. To make the question a little bit more answerable, I'm going to define it a little bit better. So, given an optical spectrum, so something SDSS light covering something from like 4,000 to 9,000 angstroms, can I predict the mid-infrared photometry of that galaxy down to chi-square 1, so down to the noise level in the photometry of the mid-infrared? Okay. So let's think a little bit about what it is that made people pick either side. So if you're on team absolutely not, the kind of mental picture that you have is something like what I introduced in the beginning, that the thing that you're seeing in the optical is stuff like stars, is stuff like heat gas from those stars. And in the IR, what you're seeing there is stuff like PAHs, you're seeing AGN dust tori, and those are just physically distinct components. They don't really have anything to do with each other. If you're instead on team, of course you can do this. Then what you're thinking is like, you're saying, yes, these are distinct components, but physically they're so tightly coupled to each other that they will end up lying on a much lower dimensional hyperplane, meaning that you can't go from one to the other. Of course, these are assumptions about the way that galaxies work, and we have to find a way to settle our differences. And as Robert Lupton at Princeton would say, you can only do this one way. We can do it with data, because data always beats assumptions. Do you want to take a picture of this?
Yeah.
There's the thing Robert says to me, but one point while we're planning, I'm using it for a lot. Data always beats assumptions. It's a good way to live your life. So the question is then, what do the data actually say? What data are we going to use? Well, we're going to use 500,000 SDSS spectra, optical spectrum here, cross-match photometry from the WISE satellites. For those who haven't worked with WISE recently, that means photometry at 3.4, 4.6, 12.22 microns. So extrapolating about 2 orders of magnitude out of radiant space from the SDSS spectrum. And then we would construct empirical mapping to go from the optical spectrum to the IR photometry, and we're just going to test how well does that empirical mapping work. One note on this, because I won't go into a lot of details in exactly how to construct empirical mapping. The only thing I will say is that it doesn't really matter how you construct empirical mapping. There are many ways to do that. If it's linear model, if it's splines, if it's small neural networks, it all gives us the same picture back. The results I will be showing are using a small neural network, but again, it doesn't really change the fundamental results. Okay, cool. So let's see some results here. So just as a reminder, if I can actually predict Wise function from the optical spectra, then my residuals in CaII space will follow these nice unique Gaussians here, and if I can't, they're going to be much more spread out. So let's see here, and okay, cool. So you definitely can predict the mid-infrared photometry of galaxies starting from optical spectra. And you can really do it down to the noise level. Like these chi-squares are really, really close to 1. So now I want to go back and think about why the very smart, distinguished scientists on my committee thought that this wouldn't be possible. What was it that made you think that this wouldn't be possible? And at least one of the culprits is the way that we tend to do SED modeling today in the Galaxy community, the way we model spectra. If you look at any paper that describes SED model, you're likely to run into a plot that looks something like this, where you're varying one component in the galaxy completely independently of everything else. And because that one component dominates some specific wavelength range, then you're varying that wavelength range completely independently of everything else. Because this picture of separability that dominates every single SED-fitting code in the world, you might want to ask yourself, well, what would happen if I take an SED-fitting code and ask it to do the same task? Of course, say I'm going to fit in the optical, and then I'm going to take the result and extrapolate it out into infrared. What do I get? And as you might be able to predict, you get something that is absolute garbage. So if you we tested two models, two very popular models, one called Kragh and one called CaII. And what you can see here is that now we are no longer close to chi-squares of 1, but instead we have chi-squares of like tens, hundreds, thousands, even up to tens of thousands. Really, really bad predictions. However, these models aren't really designed to do extrapolations. You might be able to forgive them for not being great predictors in the sense of like giving me accurate predictions. What's actually more concerning to me, coming from a statistics background, is the fact that these models are extremely confident in their wrong predictions. So if you take, for example, 100 draws from the posterior of prospect that here in blue, you can see that not only are the predictions off from the data in red, the posterior is extremely concentrated far away from the data. So you don't just get a biased prediction, you get an overconfident bias, like really the worst possible situation you can get into statistically. That's because these models here, while they are actually really good, like I'm not trying to say that these models are bad, they're really, really good. They represent, like 100 years of knowledge coming to these models. So while they're really good, they're not perfect. And every time you have an imperfect model that doesn't actually have the ability to express your data, we have a model that is misspecified to fit the data you want to fit. That model will try to take any and all 3 parameters it has to try to cover up for the fact that it is misspecified. And when you're letting all the parameters in this model very freely, those parameters will get misused in order to cover up for the model specifications. So, for example, if there is something that is going wrong in the modeling of the near-infrared stellar continuum, well, I can just take my AGN component and just invent a phantom AGN in order to cover this up. This is often what ends up happening, is that this model will make these fancy measurements of things that don't really exist just because the model is misspecified. Just to show that this is not a cherry example, we try to do this coverage test, like you actually cover the data with your posterior over the full set that we were testing on. And in general, we find that, well, yeah, they keep on being overconfident and biased. It looks like here that CaII is generally better than Prospector. I do want to warn that like this is kind of deceiving because CaII just doesn't work unless you inflate all your error bars of your data by about 10% of the flux in your data. So you make your error bar enormously larger in order to get CaII to work at all. Otherwise, it just doesn't work. This is kind of deceiving in terms of it kind of makes it seem like CaII is better than Prospector. I want to make very clear that it's not taken on me. However, one of the things I was talking about before is that the treatment of AGNs is often one of the things that ends up giving these really, really big errors when you do extrapolation out into the infrared. However, AGNs is also one of the things that you most easily be able to argue for as being not strongly coupled to the rest of the galaxy. Because after all, the black hole is very, very small, it's a very different dynamic timescale compared to the entire galaxy. It can evolve much faster than the entire galaxy. You can make a physical argument that this can decouple from the galaxy. And you often get this dust torus around the black hole. That means that you obscure all the optical light you would otherwise see. We actually have a good argument for something that is both physically disconnected and disconnected in wavelength space. But we know that we get our AGNs right. We know that we predict photometry of our AGN down to pretty good accuracy. So something must be going on. Of course, when you're at Princeton and you have a theory about something that has to do with AGMs, you have to go to the two local experts, Jenny Green and Andy Goulding, and what they'll tell you is that we don't care about the fact that you predict photometry. You have to show us that you predict something physical about the AGMs. If you can predict the bolometric luminosity of the AGMs down to 0.3 depths, we would be amazed. So in order to do this, we make an X-ray selection of our samples. We only have things that are very, very strong point source X-ray emitters, so we know that we have a good sample of AGMs. And then we use SrII to fit for the bolometric luminosity using the optical spectrum and all the infrared photometry we can find. And then we try to say, okay, we can go from the optical spectrum to that fitted bolometric luminosity with just another fitted empirical model. And the residuals we get from doing this is here. You can see that we get a typical precision of 0.33 depths. So not quite what Andy had set out for us. It's a little bit above, but good enough to earn us a very, very rare and very coveted. That's quite impressive from Andy. Of course, if you're a public user, you might be saying to yourself, this is nice to know, and it's nice to know that AGMs are connected to the galaxies and all that. But when I'm using prospect, what I care about is not deriving AGM parameters. What I care about is deriving stellar masses and star formation rates. But the reason for why you care about this is because errors in star formation rates and errors in AGM treatments are extremely strongly correlated. Meaning that if you mess up your AGM, you're likely to mess up your star formation rate inference by 8x or more. This happens pretty routinely. And so you really do need to care about your AGMs, even if what you really care about is just star formation rates. Of course, we also have to try to explain what kinds of information it is that we're using, what is it that we're leveraging that prospect that's sitting on the table, and we can make feature maps that look like this. But we have to split things up by band and by galaxy type, because otherwise the interpretation gets a little bit too muddy. So this here is for the 12 micron band star-forming galaxies. And what you see here is one of the things that we're really leveraging that prospect that's not very good at modeling is H-alpha. This is not surprising on its own. H-alpha is just the quintessential tracer of star formation and of heating of dust. Right? This is exactly what we're looking for. There's something that's heating the dust, and that's why we see a lot of flux in the infrared. However, the emission lines in this plot is only about half the total power that we get over a prospect curve. A lot of the other stuff comes from all these small lines, all the substructure here. While this looks like noise, most of these are actually identifiable with metal lines. If you zoom in on a triplet like this iron triplet here at 5200 angstroms, you see that actually get deeper iron lines. So I'm running the spectrum here in black, and then this feature attribution here in blue. Actually get deeper and deeper iron lines, you get more and more flux out of the infrared. That's because when you're talking about heating of dust in the infrared, of course, you need to get the heating right, that's why H-alpha is important, but you also need to get the amount of dust right. The way you get the amount of dust right is by getting the amount of metals in your galaxy right, because there's a covalent chain that first you have to make metals, from those metals you can make dust. So just to round off, the optical and IR are very tightly coupled. That's because the underlying physical components of galaxies are very, very tightly coupled. Most, if not all, is peaking codes and world vectors, and combining this assumption of separability with the misspecifications in those models that lead them to go to or that allow them to go to unphysical solutions in order to cover up the misspecification leads to bias and imprecision in our inference. Luckily, we can fix it, we can help fix it, data-driven models, and if you want to know more, there's a nice paper about it on the archive. And to summarize everything, it's like a grand scheme, I'll leave you with a quote from Rachel Zanson that can summarize everything here very nicely, which is, in galaxies, everything is connected with everything, is connected with everything. So, thank you.